Yeah, thank you, Max, for the kind introduction and also warm welcome from my side. So I'll be focusing more on the thermodynamics or combustion system related part of the high-speed webinar, and we are starting the presentation here with a matrix of possible combustion system. So we can see the matrix is divided into the premix concepts on the left side and the diffusive ones on the right side. Starting with the premix ones, we have different ways of introducing the fuel. So we can use a central mixer, port fuel injection, or an early direct injection. In case of hydrogen, this would be injection after intake valve closed to maximize the filling, for example. And then we have also different options for flame initiation. So positive ignition, so spark ignition, an unscavenged pre-chamber or a scavenged pre-chamber, and then pilot ignition with a micropilot concept. On the diffusive side, however, direct injection and also compression ignition is mandatory. For some alternative fuels, we will, however, need some kind of support for the compression ignition. So the outcome regarding the combustion systems would be a compression ignition concept for fuels with a diesel-like ignitability. Then we have a surface ignition concept for fuels that have a lower ignitability than diesel, but a high tendency for hot surface ignition. And then we have the dual direct injection compression ignition concept. This is how we call it. So this is a pilot diesel assisted combustion system where we use the diesel pilot injection to elevate the temperature and pressure level to then lead to a subsequent compression ignition of the alternative fuel. And last but not least, we also would have the option, which is called here DF. This means in this case a fuel sharing concept where we would mostly maintain the diesel engine and introduce some kind of alternative fuel in the port of the engine. So we are going to assess some fuels to this matrix. So these are not all the options, but this will be the fuel options that we see as most likely in the near future. So starting again here with the premix side, we see methanol and hydrogen as good fuels for spark ignition, also for the high-speed engines. So especially with hydrogen, we have a quite fast flame velocity. Therefore, in our opinion, it's not mandatory for the high-speed segment to also have a pre-chamber here with hydrogen. Then natural gas or natural gas-like fuels like synthetic natural gas or biogas we see with an unscavenged pre-chamber, as usually is the case, at least for the larger natural gas engines by now already. Moving on to the diffusive side for the compression ignition combustion system, we see on the one hand the Fischer-Tropsch diesel, but also some biofuels like HVO or FAME would be possible for a standard compression ignition engine with maybe some minor adjustments of the fuel system. And of the alternative fuels that have been assessed in the previous sessions, we also see a high chance for methanol and also for ammonia on the diffusive combustion system side with the pilot-assisted diffusive combustion system here. We are going to focus in the high-speed session on methanol, both on the premix and the diffusive side, and also on hydrogen. Ammonia might also be a likely fuel option for the future. However, we think that ammonia will most probably firstly be applied to the slightly larger engines, so more of a topic at the moment for the medium speed engines. Also, to mention to ammonia for the high speed segment, it could also be possible to apply it to a premix combustion system, but there we would need some kind of flame speed enhancer. So therefore, the ammonia part, if you are interested in that, this will be included in our presentation for the medium duty section. And today, as mentioned, we will focus on methanol and hydrogen. So starting with methanol, we've seen in the matrix, we are going to focus both on the diffusive as well as the premixed combustion system. So the diffusive one is the dual direct injection compression ignition or DDI-CI concept. And the premixed one in this case will be a port fuel injected spark ignited combustion system. So starting with the mixture heating value, the values here are compared to diesel. We can see with the diffusive methanol combustion system, we have a slight increase in the mixture heating value, while for the premix concept, we have a reduction by about 19% compared to a direct injection diesel. However, the value on the engine isn't as severe, as we also have a quite severe evaporative cooling with methanol. In both cases, considering the energy density, we would need to increase for methanol the tank volume by about 130%. And finally, regarding the fuel properties, moving on to the more combustion-related properties. On the ignition behavior, here we have ignition delay times in dark blue for methanol, in light blue for methane, and in red for dimethyl ether as a reference for a diesel-like fuel. Here we can see for methanol, if we consider the evaporative cooling, this would basically shift the ignition delay curve to slightly higher temperatures. We have a fuel with a quite good knock resistance, which is comparable almost to natural gas or methane. But with a little bit of pilot diesel assist, we can also realize quite good ignitability. So therefore, both options are quite good for methanol. And looking at the combustion speed, finally, we see we have a slightly faster combustion speed for methanol when compared to methane, which helps us for the premix concepts, but also might improve our burnout, for example, for the diffusive concept. So moving on to the combustion system, I think the port fuel injected spark ignited combustion is very common to all of you. So therefore, we are focusing here at the beginning shortly on the functional principle of the dual direct injection compression ignition concept, so the pilot assisted diesel combustion system. And for that purpose, we have depicted the process here in three main phases. So we are starting with the pilot injection, which is shortly named here with PI. In the from the step 1 to the step 2, this pilot injection is then compressed to ignite. And then in phase 2, we have the pilot combustion, which is shortly PC, and we can start with our main injection, so MI. The main injection then between step 2 and step 3 is also compressed to ignite, and we have finally the main fuel combustion and burnout in the third phase. So what first considerations can we already take from this? So regarding the engine complexity, of course, the diffusive concept is a more complex concept as well compared to the diesel engine, as we require a second direct injection system. However, compression ratio can be identical to the diesel, so we can mostly also take over the combustion chamber, which reduces the effort for modifications. And then on the premix side, we have in general a lower system complexity, as we don't have any high pressure fuel introduction anymore. But we have to reduce the compression ratio and therefore have to rethink our combustion chamber design. What do these concepts then in the end look like regarding performance and emissions? We have a short comparison prepared here based on diesel, but we are not going to focus too much on these considerations, as we will have some results from our single cylinder testing on the following slides, both for the premixed as well as the diffusive combustion system. So therefore, shortly summarizing what we can see here. Of course, mostly always for the comparison of a diffusive, so in many cases a diesel combustion system with a premixed combustion system, we will have a lower peak firing pressure due to the lower compression ratio. With the premixed one, we have a limited load range due to engine knock, but we can then in turn realize really low NOx emissions due to the lean operation of the premixed engine. So moving on to the single cylinder results. At first, we have a short introduction slide on this. So we have depicted here the engine speed, so the rotational speed over the bore diameter. For the diffusive concept, for those who have already researched on such a combustion system, some of you may know the MAN MELGI low speed engines, or also the Wärtsilä gas diesel engines, medium speed engines that are operating with a quite similar combustion principle. So what have we done in this case here for methanol? We have scaled this combustion concept basically down to the heavy duty and high speed segment. So higher engine speeds of up to 1800 RPM have been investigated by us here. And why am I stating this? So the engine speed is of course one of the major challenges for scaling for such a combustion system, as we have a pilot injection and a main injection. And in case of methanol, we also want to separate these injections. With higher speeds, the time window for these injections is getting shorter and shorter. So why do we want to separate these injections? So methanol or alcohol fuels in general are often used to boost the knock resistance of gasoline fuels, and this effect would also show here to negatively interact with the pilot diesel injection. So starting with the high-speed engines or high-speed single-cylinder engine with a cylinder displacement of about 5 liter, what did we actually achieve with our single-cylinder investigation? So we can see a load sweep here, and looking or starting with the NOx emissions, we can see we have NOx emissions below 9 gram per kilowatt hour, so we can significantly reduce the NOx emissions compared to a similar diesel engine. At the same time, we have indicated efficiencies of almost 50%, so also quite attractive efficiencies here on the high-speed engine. And the diesel share that we require for operation is at the mean effective pressure of 27 bar, which was the maximum that we've tested in this first campaign. We can see here we have a pilot diesel share below 2%. So therefore, for this methanol combustion system, we really only need a small quantity of diesel, which makes this really a quite attractive option for a methanol combustion engine. If we now also take a look at our heavy duty test results, so why are we also looking at the heavy duty as we are focusing on the high speed engines? This is due to the fact that for the heavy duty, we have actually completely redesigned our cylinder head. So we have an identical peak firing pressure resistance here to what we are testing on our heavy duty single cylinder engine with diesel. And therefore, I've prepared here a direct comparison between diesel and the diffusive methanol combustion system. So what can we see at first from these results? Considering that we have results with EGR, we can see still with methanol we have a completely smoke-free combustion, and also HC emissions are minor, while CO emissions are rising slightly with very low NOx levels, where we are having high EGR ratios and therefore a limited oxygen content, but this is similar to the diesel. So therefore, it's definitely a true diffusive combustion system that we are realizing here now. And then looking at the efficiencies, we can also see we have a increase in efficiency here in this direct comparison with the same peak firing pressure resistance of about 5% relative, while NOx emissions at the same time in lean conditions are reduced by about 60% in this case. We've also operated our heavy-duty engine with positive scavenging pressures and in lean operation, as you would normally do for most of the high-speed engines, and there we were able to achieve efficiencies of up to 52% indicated. So really quite an attractive combustion system also for the high-speed segment. And last but not least, we have also investigated premixed methanol combustion. Here you can see an example from our high-speed single-cylinder engine testing. And here we've tested with a quite high compression ratio to basically see if operation of a premixed methanol engine with large bore diameter is possible. So methanol has a quite low resistance regarding surface ignition, and therefore pre-ignitions could be a major issue to avoid basically operation of larger engines. So with our investigations, we have seen that this is not the case. So we can really also operate the largest of the high-speed engines with a premixed combustion system. In this case, due to the very high compression ratio, we've achieved only 16 bar mean effective pressure. However, if we consider that we've operated the engine with a boost pressure equal to the back pressure, we can see here quite attractive efficiencies with above 47% indicated. And at the same time, although we were operating with a quite high compression ratio, the NOx emissions are below 1.2 gram per kilowatt hour, or here 150 ppm at a relative FU ratio of 1.8. So one word also to our heavy-duty single-cylinder engine at this point. We have done investigations on this one as well, and there we have used a slightly lower compression ratio in the range of 12. And at engine speed of 900 RPM, we were able to achieve 30 bar mean effective pressure. So therefore, high power densities would also be possible with such a premixed methanol combustion system. So both diffusive and premixed methanol combustion, really attractive options here. With this, we are moving on to the hydrogen combustion systems, and we have depicted here a matrix of possible hydrogen applications over different engine sizes. So for hydrogen, we can use a wide variety of base engines, for example. So for the smaller applications, a gasoline engine might be applicable. However, for the high-speed engines, of course, it will always be a diesel base engine. And there we have a higher peak firing pressure resistance, as we can see here on the left side, but the temperature resistance is a little bit lower. If we are looking at the combustion system that we are aiming for, we can see lean or ultra lean combustion system is what we want to realize on the high speed engines. Therefore, the lower peak firing pressure resistance with the high peak firing pressure resistance with lower temperature resistance is suiting this kind of combustion quite well. What will the combustion system overall look like? So we think that a low or mid-pressure direct injection or a low-pressure port fuel injection is most likely. So low-pressure DI, we say this would be below 30 bar, and mid-pressure DI, this would be below 60 bar. As stated, combustion will be lean or ultra lean. And there we can already see that the boosting system will be one of the major challenges or major points of differentiation, as this is also so the richer relative FU ratios are our limit basically regarding pre-ignition and knock, and therefore this is also determining somehow our load range that we can achieve. After treatment for many applications can be done without a system, but for the most stringent ones, an SCR system will be necessary. So we are going to have a closer look into the hydrogen internal combustion engine on this slide. Here we have summarized two of the major challenges regarding the hydrogen internal combustion engines with results from our testing on a heavy duty, but also a medium duty engine. Both engines were operated with cam timings that are optimized for cylinder filling. And starting with the heavy duty single cylinder engine results on the left side, we have a direct comparison between a direct injection and a port fuel injection methanol concept. And the first thing we can see here, quite obvious, we have a much lower boost demand, of course, with the DI where we've injected after intake valve close. But if we are moving on to the NOx emissions and also the efficiency, we can see we have major drawbacks regarding the mixture formation for the DI, at least in this early stage of application. To the efficiency, we have also operated here at a boost pressure equal to the back pressure. So the advantage regarding boosting is not considered here. So mixture formation optimization will be one of the key challenges for the hydrogen internal combustion engine. And the aim would be to really match with the DI the values of the PFI regarding NOx emissions and also efficiency. And then finally to this slide, moving on to the medium duty engine. On the right side, we can see here a load sweep. So load range is definitely a severe challenge for the hydrogen internal combustion engine. And we can see here on the first diagram, the relative FU ratio is enriched with increasing load, as the boosting system will never be able to always operate at a relative FU ratio of 4 or something in that range. And therefore, it's also a major task to optimize the compression ratio in regard to shift the limitations regarding pre-ignition and knock to where we really want to have our maximum mean effective pressure. So in this case, we have done one optimization loop from the base compression ratio of the natural gas base engine to a optimized compression ratio, which is obviously a little bit lower. And there we were able to widen the load range achievable from about 16 bar to around about 20 bar. And also this, of course, improves the transient performance as we then have a little bit more potential for enrichment. So we've taken a look at the challenges for the hydrogen internal combustion engine, but we are, of course, always interested in solving these challenges or improving on our combustion system. And for that purpose, we apply a comprehensive tool chain that we've also validated with our test results. So we are starting from 0D with an entrainment model where that we can use to pre-optimize the compression ratio. Then 1D gas exchange simulations to optimize the valve timing, but also the turbocharger layout. On the 3D CFD side, we are starting with mixture formation simulations. For example, injector spray targeting and injector location. For that purpose, we've also performed pressure chamber tests to validate the spray models, which is really very important to the mixture formation optimization. And then finally, of course, we are also performing 3D CFD simulations where we can also optimize parameters like the piston bowl geometry, and we can also use this as an interface to the engine mechanics, for example. So looking a little bit more in detail to the mixture formation, we can see here on this slide, we have a lot of parameters that we can use to really influence our mixture formation. So we can, for example, use the port design to increase swirl level, or maybe also get some tumble in. However, for the flat cylinder heads, this is of course not the main charge motion mechanism. Then we are also inducing turbulence with the injection. We have some turbulence induction with a squish flow from the piston design, depending how large our engine is. So at least for the spark ignition engine, we are, of course, always trying to keep our piston bowl compact. We can also design the piston bowl to redirect the spray to basically interact with our hydrogen injection. And then we also have to think about wall interaction. So with hydrogen, we need to avoid accumulation of the fuel on walls. So we have to consider the Coanda effect, for example, to avoid accumulation at hot surfaces, for example, or also high hydrogen concentrations at wall proximities, which could possibly lead to embrittlement. So yeah, how does this look like, or what do we do there? So we have 3 examples cases for the mixture formation here. So these are just examples. These are not the optimized solutions, and we are having a look here on a central injection without swirl, a side injection without swirl, and then also a side injection with a swirl number of 1.5. So starting with the central injection, we can see we have a quite even spread of the fuel, at least around the center axis, which is continuing with the crank angle. But we have a poor entrainment at the edges of the combustion chamber. And what we have to keep in mind for a flat cylinder head without significant entanglement of the spark plug and also the injector, it will be very difficult or mostly impossible for most of the high-speed engines to implement both an injector and also a spark plug in the central position. Therefore, moving on to the side injection cases, we can see here on the first one without swirl, this is really a major challenge. So we can use the piston bowl here to redirect the spray, and possibly we can also create a rich spot at the spark plug proximity. However, it will be quite challenging to really get a uniform distribution of the fuel over the combustion chamber that we want, especially regarding NOx emissions. And then finally, moving on to the case of the side injection with swirl, we can see that the swirl is basically for the short injection duration that we are looking at here, not turning the flow fast enough to really lead to a significant mixing over the entire combustion chamber. So Therefore, just using charge motion or high charge motion levels is not sufficient, and we really need to optimize this with all the measures that we have. Which brings me to the final slide. We will, for the cases on the previous slide, take a closer look to the concentration close to the spark timing. So we see for the central injection case, we have a rich, or at least a richer concentration in the piston bowl, which is good if we could also ignite the mixture in the piston bowl. But as we've stated, this will be very challenging for the high-speed engines, and then for the side injection cases with this preliminary preliminary design, we can see we have still very lean zones also in the piston bowl, which makes the operation quite challenging, and therefore also prolongs our combustion duration, but also increases the NOx emissions. And to really optimize this in a good way, we need to consider all the parameters that we have. For that purpose, we've depicted here the tumble generation by the H2 injection on the right side. Just to show you, we really have to think about also the interaction of our hydrogen injection with our charge motion, and for that, of course, validated models are one of the key things that we need for a good result of our optimization. And with this, we've talked about methanol and hydrogen for these high-speed applications, and I've sadly already reached the end of my section, of the thermodynamics related section, and Stefano will now follow and tell you more how these requirements regarding the thermodynamics do affect the base engine design for the future high-speed engines. So thank you very much for your kind attention. It was a pleasure, and I'm looking forward to your questions afterwards. Please, Stefano.
Hello, Arne. Thanks a lot for this kind introduction. So Arne has introduced a lot of different combustion system, and of course we have our engine mechanic that has to fulfill with all of them. So now I made here a sketch where we see different criteria starting from base engine, boosting, fuel injection, exhaust after treatment, and controls that is deployed on the different fuel types. So here I present here a fuel that we discussed mostly during this couple of hours. So one is hydrogen, natural gas, and both the combustion system of methanol premixed and diffusive. Of course, what we can say that different fuel will have different requirement in the base engine. So, for example, hydrogen will require lower compression ratio, so generally lower peak firing pressure. But we know that lower peak firing pressure, lower compression ratio will also generate lower BMEP. And this means that the power density of the engine will decrease. And how we can recover this? For sure, we can increase the displacement. But we have also to keep in consideration the package, because you know that the high-speed engine are very famous also to be very high power dense and very powerful machines. So in the other end, for example, when we go to methanol, in the complete other side, methanol diffusive, we can keep more or less the same feature of a standard diesel engine, and of course a high peak firing pressure and a high compression ratio similar to diesel are beneficial to increase efficiency. And also, if you go down, and the boosting is also another big topic. So, for example, in hydrogen, we know that the boosting demand are high. We run very, very lean or ultra lean. And especially if you want to go for a non-after treatment system solution, we need to have ultra lean combustion systems. So this will for sure increase the demand on the boosting side. But in the other end, diffusive methanol, for example, will have a similar to diesel performance also from the boosting system requirement. For hydrogen, we need, so we have discussed about low pressure direct injection, the spark plug ignited. In the other end, for methanol, we have an high pressure direct injection with pilot support. So this will also increase the challenge on the cylinder head. We know that the cylinder head of the high-speed engine are quite limited in space. And of course, if you want to have a one-fit-all or modular architecture, this will pose significant challenges on the engine design. And then at the end, exhaust after treatment controls will strongly depending on the local legislation. For sure, what we know that will be some of these, especially in hydrogen, we have quite high hopes that non-SCR solution will be also possible. But nevertheless, for the most strict or close to zero emission, especially also considering transient, most likely an SCR will be needed. as well as for diffusive combustion. For sure, an SCR will be a topic. And here I will show you later also some more detail. For sure, there is also very strong discussion regarding particulate number, and most likely in future also this will be limited, and we have to consider also some particulate filter. Then in terms of controls, also advanced air path controls will be very important, especially in the combustion of hydrogen, to increase the transient behavior, but at the same time not to occur in knocking effects. Therefore, also advanced control will be very important. If now we do, if you want to achieve a modular architecture, so what we can think about, here I plot a graph where we see that the power, here it's the bore, let's say from 170 to 185. And what is the idea behind here? If we keep, if we consider a stroke of 250 millimeters, so that at 1800 RPM generate a piston speed around 30 meters per second. And if we consider the higher demand in terms of peak firing pressure of a diesel-like engine, and a lower demand of, for example, a hydrogen engine, we could consider to create an engine, a modular engine architecture where we can allocate in the same, for example, block base engine, the same, let's say, different bores, for example, 170 here and 185, maintaining constant the peak firing pressure on BMEP level. Here I made an example for 8.6. So with this system, we could generate 20% more sweat volume in the engine. That will partly compensate the drop of power due to the fact that the BMEP reachable with this new fuel like hydrogen will be lower compared to diesel. And the advantage of this idea, for example, is that we can keep constant the cylinder bore pitch that drives more or less all the auxiliary of the engine, the exhaust manifold, and many other features. So with this concept, we could realize in the same engine architecture two completely different bore, let's say at maintaining a constant stroke, and generate different bore pitch, let's say, at the constant bore pitch. And this will for sure give us the possibility to recover part of the power loss due to the different fuel by a modular architecture. This can be, we have to pay a little bit this, so it will not come for free, because of course all the cranktrain components and some other components that will be modular will be slightly bigger compared to a standard 170 millimeter high-speed engine. So we consider here that we will have a weight increase for example, for the smaller machine of about 8%. To have this commonality, but this could be anyhow a very good, let's say, way to do it, because with one modular architecture we could cover different displacement. How we can realize this in practice, for example, one possibility could be that we do a modular casting architecture where we can modularly change let's say the cylinder domes or the cylinder cores, or in future we could also think to introduce water jackets design like a medium speed, like on the high speed class. So to exchange bores, let's say more in a modular way. Okay, another point that we discussed before, so it's also the let's say the need in boosting. So we know that today most of the high speed, especially for marine, are turbocharged one stage because it's a compact solution, and some of them are also sequential driven. So here, for example, we see a 20V engine that is with four turbochargers, let's say single stage. But due to the high demand of boosting in future, especially in direction of hydrogen, we could also think about it in future. We would need some two-stage possibilities on the engine. This for sure, as you can see, the complexity in the right side of this picture or two pictures will increase significantly. The number of cooler will increase. Of course, also there will be a drawback in weight. But nevertheless, we will have the higher boost capacity that maybe is required for these new, let's say, fuels. And what is at the end the discussion here? So it's very well known that when we started to design a new high-speed engine, there is always the question: what is the best V angle? It is a V90, V60. So of course there is not a right or wrong solution, but this depends a lot on the customer requirement and the application that the engine has to at the end to be used. But of course, since the boosting requirement will be anyhow even higher in future for some fuel, we have to consider that in case of a V60, for example, like it is in the left case, the space, let's say, required, the space utilization on the top will be more limited, the space availability in the middle of the V. Therefore, the engine will grow up in height, while a V90 engine, let's say, will provide more space in the middle of the V, also to allocate a more complex boosting system. And this, of course, will lower the engine height, but with some drawback in the engine width. So at the end, also the message of this slide, there is not a right or good solution, but there is also considering just a simplification, just consider the V angle for the space reservation for the boosting system, for example. This also poses quite a big, at the beginning in the concept phase, quite a big, let's say, thinking to understand what are the best fitting for the application. Of course, the V angle is not driving all the turbocharger position, but it's clear that the V angle is also very important for many other parameters like torsional vibration, like for engine mechanics in general, like, for example, the crankshaft layout with different layout for the like symmetric, semi-symmetric, or counterweights. So at the end, so we have developed a quite holistic approach to define the V angle, where we start from engine overall dimension, architecture of the components, engine balance and mechanical load, and then vibration. So we can overall rank these different criteria for importance. Also, for example, considering the number of cylinder variants that the final engine has to realize to define the best let's say engine let's say architecture that will fulfill the customer application. And also, if you stay in boosting, what we also Arne said very clearly that, for example, in case of different combustion systems that are here in the middle, we will have different requirements in terms of boosting. If here in the picture you will compare a standard diesel engine single stage turbocharged, and in red we compare the BMP level as 100% and also the boosting as 100% of the requirement for diesel. Here we see that different combustion system will require different boosting level. For example, in methanol, we can say that the boosting is very equal to diesels or very similar in methanol diffusive combustion, while, for example, in hydrogen direct injection, we see that in general, compared to a diesel engine, we will have a drop on the BMP level that it is possible to achieve, mainly due to knocking problem, but even with an increased boosting demand. At the other end, also methanol PFI and natural gas PFI, for sure, we lower the BMP of the engine, but at the same time, we'll also lower the boosting demand because the BMP level are lower. And the limitation here also comes from mostly from knocking. So here we have plot, for example, different turbocharger concept for a diesel engine. So we know that the power density, but also acceleration profile and also the torque reserve on the high-speed engine are a very important feature of this engine. And here, for example, for a marine application, we have plot a standard diesel engine in the bore range of 170 millimeter that can reach more or less a BMP of over 30 bar, so very modern design. And we see what are the feature or the torque that we can realize with different boosting system. So, and here we also see in green, in the green line in the middle, we see the propeller curve that we can realize. So that at the end, with the small reserve, torque reserve, also in the last point to achieve maybe even a 110% load power. So we see that, of course, the torque reserve it's increasingly depending on the complexity of the turbocharging system. So, for example, here, if you go for one stage, we will have a significant drop of the torque reserve. If you go to a two-stage conventional, this will improve. But of course, the best would be to, so for in this case, to have a very high low-end torque reserve and also at also very low engine speeds, a one-stage sequential will be most likely the most beneficial system. And here, if you plot an equivalent hydrogen engine with two different combustion systems, so in the top line we see the DI and the PFI. Here we see the gap that is generated. So we have to lower for sure the capability in terms also propeller because the engine will generate less BMP. And here we see this gap that is driven mostly by the boosting system because, like Arne also showed before, we will always have a gap between DI and PFI in terms of power density. And what is also very important for high speed, so it's also the acceleration, the fast transient behavior. So here, for example, we have developed at FEV a very quite complex model that we can elaborate in transient a response of different turbocharging system to optimize them. both in terms of controls, but also in terms of turbocharging dimensioning. Here, for example, we do an example from a simple one-stage turbocharged system to a two-stage sequential system, again for a multi turbocharger engine, so V20 considering 4 turbocharger. And the model that is behind here is a ship model, for example. So we are considering a ship model with a linear behavior between engine speed and ship velocity. And here we are comparing different acceleration profile of the ship, of the complete ship, with different turbocharging system. And as of course you can see, and how is it thinkable, the more you increase the complexity on the control and the turbocharging system, the more you can reach very fast acceleration. So here the blue line, for example, that is on the top of the right graphic is showing a two-stage sequential, so very complex system that is a combination of two double-stage concept, let's say. And the most common use one-stage sequential is also more or less one of the optimum system. And then, of course, we have a conventional two-stage and even a one-stage only engine at the end with the green line. And for these two, of course, we have also had to optimize slightly the smoke limitation. Otherwise, the time would also insist a little bit longer. So as you can see here, this is a quite important matter for the high-speed engine. And we have a very good model that where we can simulate different transient behavior at same application, also to define the best turbocharger, not only in matter of gas exchange, so stationary point, but also in transient. So when it comes now to fuel injection equipment, so the new fuel will also pose significant, let's say, challenges for the fuel injection system suppliers. And here we try to make some ranking about some mechanical criteria like lubricity, corrosivity, cavitation, embrittlement of the material for the injector and the high pressure provision. Normally it is, for example, an high pressure pump. And if we concentrate now on the direct injection systems, for example, and we consider diesel as a state of the art, let's say, or a modern injection system, 2,500 bar. For a methanol DI concept, we considered more or less a 1,000 bar fuel injection system, while for an hydrogen, a direct injection pressure of more or less below 60 bar. And what we can see that in both cases, what happens that the lubricity of the fuels drop dramatically compared to diesel, and this of course create a problem on valve seizing, for example, or needle impact or whatever. And also the cavitation, for example, in methanol, we have also issue regarding cavitation. So cavitation in nozzle and also in the control valves of the high pressure pump. While in hydrogen, instead, we don't see cavitation issues, or limited at least, but the embrittlement issue is for sure something that we have to consider. So in the material selection, for example, for those components, the embrittlement has to be considered, especially for to have a longer reliability time. And when we go to the high pressure provision, for sure we have here again an issue with cavitation control valves. Lubricity will also pose, so we will have to we consider also lubricating oil and also corrosivity of the methanol. So this is also corrosive material. But while in the hydrogen case, if we consider a liquid storage, we have to deal with the cryogenic systems with all the issue that they concern, let's say. Therefore, so this is just a slide very similar to what Arne presented. So there is not. So here I present, for example, in hydrogen, the selection of the injection system. It is becoming even more complex than today. So because we have to consider all the parameter that we have in the engine, so the location of the injector, the type of cylinder head, if it is a flat or a kind of small pent roof with side feeding or central feeding or whatever. So we will have a very high complexity overall. Also injector type, the flow guidance, injection timing, the pressure that we are discussing about, and the profile. And all together will, for example, for hydrogen, will play a major role regarding mixing. And that's why there is not one good or right at the moment, but we have to to have an holistic approach where we consider all these several aspects of the combustion system and of the injection system, and the strong cooperation between the fuel injection system supplier, the engine, the engineering side that is dealing with the CFD analysis and charger motion design. So these have to be even more intensified, even more than before. So Another very, very important aspect that becomes very critical are also the controls. So at FEV, we have developed a very modular architecture for functionalities. And we have a kind of catalog, let's go like this in a simplified way, where we can select different control systems, let's say, and what is strong in our side that we can easily integrate them in a RCP system, so a rapid control prototyping tool, where we can completely bypass the original, for example, if you want to start with an existing engine, we can bypass the original ECU system, and we can control the engine with this, we can completely control the engine with our RCP system. And this will enable also, for example, not only a very rapid availability of the engine, to start with some basic performance evaluation or combustion development or even calibration, but also to select what are the best control functions that the engine should be available then at the end during the industrialization phase. And of course, those functions are also possible to be integrated, so they are at the kind of maturity level that are possible to be integrated also in a full engine scale, let's say a release. But of course, then the cooperation with the tier one supplier of the ECU has to be increased, because we have to integrate those functions in existing architecture. And of course, at the beginning, we are quite independent. So you see from this kind of triangle on the right. So at the beginning, we are quite independent. We can fast release a function, control feature, reduce control feature, or increase them. But then at the end, we have to deal also with the software integration, and therefore the tier one supplier will be very important in this phase. Here, for example, I can discuss about controls. So here it's again regarding hydrogen. So the control logic will become very, very important. And here we, for example, I want to show you what is the importance of a control features for the transient maneuver. So we know that when we create a transient maneuver with an hydrogen engine, the NOx emission are increasing quite dramatically, especially if we allow enrichment. So the enrichment allow to have a faster transient, but in the other end, our NOx emission are increasing very much. So therefore, we have to find a way to introduce smart controls that are practically where we can define the better trade-off between NOx emission and transient performance. And to do this, here I can show, for example, a graphic where we have several ways to go from a point. So here we want to realize a load step, for example, from 0 to 12 bar, for example, BMEP, in three different steps. So let's say we have a kind of a load increase, load jump that is more or less a mechanical jump that we have always at the beginning of every load step. And then where the boosting will play a role, boosting and combustion grow up with power over the time. And here, for example, we see different strategies to realize this. If we go for the approach that zero load, and then we go for, let's say, a kind of a very, very limited retardation and go directly from point 1 to point 2 and then 3, we can be quite fast. But in the other end, we are increasing very much the NOx emission. So the NOx emission go very, very high. We could also think to go even faster than this way, to go for the red line, where we do a kind of advanced control, where we start to, let's say, retard the engine to go very close to the knocking and pre-ignition line, and then go up close to the line to reach the point 3, and then finally the full load to stabilize. But of course, also in this case, we'll be very fast with the transient maneuver, but we will also emit quite a significant amount of NOx. And what we can do with our control, we can dynamically control the retardation of the ignition from the point 1 to 2 here in a very dynamic way, let's say, and select the best retardation that will enable a very fast transient, let's say, but at the same time, keep the NOx under control. And all these functionalities are, let's say, quite specific for hydrogen compared also to what exists today for gas or gasoline. So therefore, these are very important if you want to realize engines that are also starting from an ultra. Of course, here we are discussing about an ultra lean baseline. So these are very important because this enables to have, of course, very low emitting engine overall in stationary point, but also very attractive in terms of NOx emission during transient maneuver. And so if you now discuss finally regarding emission, so what we can see that, of course, there will be the emission will depend strongly on the application and also on the emission legislation. So like Andreas has explained a little bit at the beginning, there will be a lot of different regulations. So some are global, like IMO regulation. There will be a lot of local regulation, and there are also non-road mobile machinery, for example, stage 5 or post stage 5. And the different combustion system will, let's say, will trigger different engine pollutant compared to what we know today. So today we know very well known NOx, NPN, and particulate matter in terms of emission for a diesel engine. When we go towards, for example, hydrogen or methanol, so the NOx will remain still an issue for hydrogen, even though we have said also before that we can realize very, very low engine out emission in terms of NOx also with the hydrogen. And methanol, for example, we will have also HC emission and also formaldehyde emission. So all these complex different combustion system at the end will trigger different kind of exhaust after treatment system. But what is also a common approach that is also anyhow simplifying our life is that the urea-based SCR will work more or less for all the combustion system application when we have to discuss about NOx reduction. And in future, if the particulate number will be limited, so these engines are, for example, hydrogen or methanol, they don't have any issue with soot. But of course, the particulate number will play a role because this engine has anyhow oil still needed for lubrication. So the oil can for sure generate particulates, and the particulate number in the future will, as already today, a quite strong focus, and most likely in the future will also be regulated. So we could also think that in future a particulate filter also for those engines has to be used, but of course with I would say less complexity compared to today these particulate filters, for example. And now I want to show you, for example, for hydrogen, we have made here a kind of different, so we have made here an analysis of different conventional zeolite. For example, this is a zeolite approach. So with different zeolites, so this is iron, copper, or iron zeolite for another species. And what we see here compared to the dotted line and the solid line for all the three different zeolite concept, that let's say the conversion efficiency of a hydrogen engine is very similar to a diesel application. Of course, there are some side reaction here for some specific zeolite, but in general, we can assume that the conversion efficiency is very similar. And this, of course, give us a very good, let's say, hint that in the future we can continue to use our today well-known SCR system in case of need. In the other hand, we could also think for the future to introduce an H2-based SCR. This, of course, will not need an additional fluid, like, for example, here it is here ammonia. But in this case, today, the technology is quite at the preliminary stage. So the temperature window where this system has a reasonable DeNOx performance is very limited. And different zeolite, this window also shift at different temperature condition depending on the zeolite that we choose. So for example, here we can see that if we would combine in future a kind of mixing zeolite that combine the performance of all three, we could include let's say we could increase the window where the SCR reaction occur, let's say, but we are still not in a phase where we can think to industrialize. Still some research is needed in this case. And also what we have to consider that during this reduction phase, you see that the NO2 production is also increasing. So this is also a side effect. There is a side reaction occurring. So therefore, we have also to consider that in future, let's say this can as also to be tackled as an issue, because N2O will also be regulated most likely. So then all in all, so this is my last slide. So I would say that clean, compact, and power-dense defossilized high speed is possible, let's say already today. So we see that a lot of technology are available or are in development. So we are very much excited to go on for this defossilization path. So thank you for listening. And Max, give back the word to you.